Okay guys, in this video clip we're going to talk about chapter 18, introduce it, get ourselves into some stuff with equilibrium and reaction rates. Alright, so before we can go too much further into this concept, we need to talk about what actually happens at the molecular level when chemistry happens. So we got to think about collisions. Okay, so first thing that happens is, for a chemical reaction to occur, two particles have to collide with each other. Now, when they collide, you can't just have any type of collision. You have to have two parameters that must be met. The first parameter is they have to be in the proper orientation, okay? Which means that they can't just hit each other anywhere. You need to actually collide with the right atom facing the other right atom, or the right atom hitting the right bonding area to actually break apart bonds. So, for example, down here, we see that the white sphere, if it comes in and collides with this double bond, can actually break this double bond up and create chemistry. But any other type of collision that happens between these particular two molecules would not create chemistry. So our first step is you need to have the right orientation. Now, we don't have a lot of control over orientation unless you start getting into organic chemistry and manipulating molecules. But for a typical general chemistry scenario, what we try to do is just have as many collisions as possible. That way the chances are, or the probability of the right orientation goes up. Now, once you actually have the collisions happening, they have to have enough energy to make that reaction happen. So the second parameter is having enough kinetic energy. If you look at this graph, you should recall this being a Maxwell distribution curve, where if you take a sample of particles, they have a distribution of energy, or basically speeds, at a given temperature. So here's your number of particles on your y-axis and energy on your x-axis. So if there's a point at which you have enough energy to react, it would be this green line. Okay, we call this green line the activation energy, or the point at which there's enough energy to actually activate the reaction. So in this particular scenario, if these are all the particles that exist in a sample, and all these ones that are light blue, they don't have enough energy to actually react. So it doesn't matter what their orientation is, they're just not going to react because there's not enough speed there. There's not enough violent enough collision to make this thing happen. However, we do have a few particles over here that do have enough energy to react. So this reaction can run, but it would run very slowly and actually would diminish very quickly over time because these higher energy particles would leave first from that reaction. Now, part of the job as chemists is find a way to make this graph either shift to the right so we get past this line, or maybe take this line and move the line to the left so it takes less energy to make these things happen, okay? And that's some things that we're going to talk about in the upcoming slides, okay? But all of this comes back to collisions. Without collisions in the right orientation and with enough energy, you can't get chemistry to happen, okay? So the first step of this process, looking at energy in particular, is what is this magical amount of energy we need to get the reaction to run, okay? We call that activation energy, okay? It's our minimum amount of energy required for the particles to react, okay? All chemical reactions, I'll say that again, all chemical reactions need energy to start them because it takes energy to break those bonds that are there currently, okay? So every reaction, whether it's endothermic, exothermic, spontaneous, non-spontaneous, it does not matter. All reactions require energy input, which we call activation energy, to start them. So if you imagine you have reactants here, and they actually increase in energy, or they get some energy, they get through the activation energy, which is the EA, energy of activation. So here's your energy y-axis. Once they get to high enough where they're on the top of this peak, then they become what we call the activated complex, which this isn't a transition state. This is where the bonds are being broken. This is where there's enough energy there to start to split things apart. The collisions are actually creating new bonds, breaking things apart, and if things are favorable, then they'll fall down the backside of the hump and create a new compound. Now, that hump may fall all the way down to here and make products, which then we'd have exothermic, or they may only fall part of the way down and be above the dotted line, which then you'd have an endothermic scenario, okay? So it doesn't matter which way they go, they just need to get up over the hump to make this happen. Now you'll notice on this graph, we have two different lines. We have a blue line and a red line, okay? A lot of reactions can run uncatalyzed, which means they just happen on their own. However, some reactions don't work very well uncatalyzed, so you need to find a way to speed them up. So when you catalyze a reaction, what happens is you actually are able to make that reaction happen faster. Now, one incorrect way of describing why this works is I'll sometimes hear a lot of students say that a catalyst lowers the activation energy. which is saying that this blue line gets scrunched down to where the red line is at. And that's not actually correct because the blue line never gets moved. Okay? If you have an uncatalyzed reaction, that blue line stays there and exists forever in that reaction. However, if you add a catalyst to it, you actually can find an alternative way for that reaction to run. Okay, so I kind of attribute this to like a mountain biking or like a hiking type of scenario where if you're climbing a mountain and you're in a big group of people and you say, okay, we want to get to our campsite, which is way down here, but first either we go over this mountain or we can take and go over this shorter mountain. Which way do you want to go? Well, the people who have less energy, who aren't as in shape, who aren't as fit, they'll take the easiest route. So the majority of people will take the easy way. However, just because this way is easier doesn't mean you won't find some people who won't want to take the harder way and take the harder route if they happen to have enough energy. And that's the same thing in chemistry, where particles with enough energy, they'll take this pathway just as quickly as they'll take this pathway if they have the energy. But if they don't, they had to go through the red route instead. Okay? So with catalyst, a better way of saying what a catalyst does, it speeds up a reaction by providing an alternative pathway or a different route that has less activation energy. Okay, so we shouldn't say it just lowers it. It's an alternative way of making it happen instead. Okay, so if we take this idea to talk about speed of a reaction and kind of what goes on there, we want to talk about rates. Okay, so rates is kind of a fancy word for speed or velocity or that kind of stuff. And we have some different factors that can play a role here. Particle size, temperature, concentration, pressure for gases only, and then of course catalysts. Now, in class, we do some demonstrations with all this kind of stuff with lycopodium and antacids and those kind of things. But we'll just talk about them in the video. So particle size, okay? So for every one of these scenarios, we're going to try to talk about what we would do to make it be faster, okay, or to increase the rate, okay, and then obviously the opposite would slow it down. So for particle size, that's an inverse relationship. So you want to have very small particles because the more particles you have, or the smaller they are, the more surface area you have. The more surface area, the more collisions you get. The more collisions you have, the more likelihood you have enough energy and right orientation to make it happen. Okay, so to get a fast reaction, you want to crush things down into the smallest possible particles you possibly can. Okay, you don't want to take the mass away. You want the same amount of mass, but with smaller particles. Now, opposite of that is temperature. So if you want a reaction to run faster, you usually want to heat it up. Okay, so if you give things more energy, make them hotter, the reaction runs faster because they now have more energy, so a greater proportion of them will be able to react. Okay, we actually can look at this graph to kind of show that. So we have temperature 1, which is cold temperature, temperature 2, which is a hot temperature. So if you look, if this line represents the activation energy or the energy it takes to react, the hotter particles have a much bigger amount of particles that can react versus the colder one, which is much smaller. Okay, so the hotter you are, the more energy you have, the more likely that your collisions are going to have enough energy to properly react. And then we go to concentration. Okay, so to speed up a reaction, you want to have higher concentration. Okay, for the same reasons, the more concentrated you are, the more particles that are there. The more particles that are there, the more likelihood the collisions are going to be the right type of collisions. So again, we always go back to collisions in terms of what this thing affects. Now with pressure, because gases aren't in a solution and they actually are dependent on their size of their container, the more pressure you have, the more particles you can fit into a smaller space. So once again, more particles in a smaller space means more collisions means faster reaction. And of course the catalyst. Now we've already talked about a catalyst, but just kind of a quick reminder that catalyst provides a different pathway that allows that activation energy to not be necessarily be here, but maybe be a lower value that they can use instead. So by having a catalyst present, we have a different activation energy that's allowed, which then allows the reaction to run faster also. Okay? So these are your basically 5 different ways you can speed up a reaction. Now obviously, if you reverse those kind of things, big particles, cold temperature, dilute solutions, low pressure, no catalyst, that would slow the reactions down in opposite of there. Okay, so here are 3 videos of different reactions that run at a very specific speed, okay, which we call clock reactions. Okay, so that's the first one. What you saw there is basically iodine being produced with the presence of starch. And this one's kind of cool because if I change the concentration just slightly with these, I actually can get these to change the color very quickly, but in sequence. Okay, so the next video kind of shows that sequencing.
Wait, yeah, it's done. Okay. You're rolling.
4, 3, 2, 1, go.
Which one's first?
Left.
Left. 3.
Yeah.
Oh, 5. Oh. This one.
All right, and then finally the third video takes it to one step further, where not only is it a clock reaction because it happens in a certain amount of time, but it's an oscillating one that actually allows the reaction to run back and forth in two different directions at the same time. Now, eventually that reaction would settle on being a dark blue color, but it does oscillate back and forth. Okay, so that brings us to the kind of the next piece of this puzzle, where reactions run at a certain rate or a certain speed, but then also a lot of reactions are actually reversible, where we actually can have them run in two different directions at the same time. Okay, so when we have a reversible reaction, what we say is that we use a double-headed arrow, and what that does is it allows us to have a reaction that occurs in both directions simultaneously. So you can have sulfur dioxide and oxygen making sulfur trioxide, and you can have sulfur trioxide making these two. Okay, when we do that, or we have that, we have reversible reactions. All reversible reactions start with everything being a reactant like this, and then they start to make product. And then once you make your product, you start getting this balancing act between the two things. So that balancing act is what we call as our equilibrium. Okay, so once you are at equilibrium, you have a little bit of both there. You have your reactants there and your products there. Now, the equilibrium can shift depending on what parameters we put into it, but all reversible reactions have to have some sort of equilibrium, or a point at which the amount of each one of these things is stationary and the rate of transfer is equal. Okay, so we're not saying that you're 50% reactant side and 50% product side. We're saying that the rate of transfer or the shift becomes equalized over time. Okay, okay, guys, we're going to end it right here. The next slide gives you more detail onto equilibriums. Thank you.